in a way that our particle is close enough to it, so it will have a far distance to the nearby particle at the surface. This distance is not comfortable to them. They want to be this close, but it's too far. So just like a spring, they will attract each other, and this attraction will create a tension on the surface. This tension on the surface will then pull up the water. That is the source of this capillary effect. Okay? So, not all the fluid is like this. Water has a strong surface tension, but this spreading of particle at the surface depends on what type of particle inside the water and also on the interface. If you are in the air is going to have some particle bouncing to the water and bouncing out. So this bouncing will be different if it is oil on top of water inside instead of air on top of water. This tension is a property not just the water, but a property of this interface. The way particles align will be different if you are having oil on top instead of air on top. Now, because the particles at the surface want to attract each other, the surface itself will have a tension holding things together. So if I have a tube like this, and another tube on top, and I somehow created a water curtain like this, so this is made by water. This water will have two surfaces, one in the front and one in the bottom, one in the behind. There's a surface behind it and a surface in the front. Each of them together will create a tension force. Okay? Now, if I look at another water curtain that is wider, the width of this curtain is L, and the width of this curtain is 2L. Even though I'm drawing it like this, but this tension does not happen at the edge, it happens at the surface. I draw it at the edge because I want to show you there's tension from the surface behind here and the surface in the front. Okay? So now, if I have twice the amount of width, it's like having two curtains. Then, if originally the tension from one surface is T, what will the tension on that from the surface be when it's 2 times what? 2T. 2T, good. And the one in the behind is also 2T. Okay? So this tension from the surface is not the property of the water itself, but also how wide the water curtain is. Therefore, when we see something proportional to each other, we define the proportional constant to be something important. And this thing will be what we call surface tension. Surface tension is not a tension. It is the tension the water can create per unit width. The wider the curtain is, the stronger the total tension. So we want to have a proportional constant to be the property of the water-air interface. If the air is not air, but like argon, helium, different type of molecule, if you are using different type of fluid on top of water, the way those particles affect the surface will be different. So surface tension is not a property of a water, but the water and the other fluid surrounding it. It is a property of interface. Okay? And this is gamma. This is not R, this is called gamma. It's a big vector. We use that for surface tension. So, if a water curtain with L can create surface tension of T, which equals gamma L, then how big of a tension can surface tension create in these two? The length that the surface is contacting the wall in here will be the circumference of this tube. So the tension will be surface tension times this circumference. Does that make sense? But this tension is not pulling the water directly up. It's pulling it with an angle. So let's cut it in half. The right surface tension will be surface tension. So the right tension, the tension caused by water on the right half will be surface tension times the half of the circumference. So it will be half of 2 pi r. R is the radius of the tube. And how do I make r look different than gamma? This is r. This is gamma. Let's do exactly the same. R, gamma. Okay, all right. Now, the tension on the right is going here with an angle theta. This theta and this theta is the same, so that's why I put it on both sides. The tension from the other side is also making angle theta. These are the total force on the system, which the horizontal component is pointing in opposite direction, but the vertical one is pointing in the same direction. So when you add these two forces together, the horizontal one cancels. This cancels this one, and the result will be a total force that is twice as big as T times cosine theta, because this is the adjacent side of this hypotenuse. The horizontal component of these two tension will cancel. You know it must cancel because the water rise up is not going right or left. So there must be no horizontal force. And the vertical component is cosine. Okay? So a T is surface tension times half of the circumference. So 2T times cosine will be 1/2 times cosine. So it will be 2 pi r gamma cosine. And that is the total force that the surface tension is pulling up. We call that Fc for capillary force. So that's how big the force a capillary tube can get from surface tension. Okay? So when I look at this force, I want to know what is the equivalence pressure it creates. If I look at this, capillary, the pressure at here is P air. the pressure at here should also be P air because it is connected with open air. But we learned that the pressure at here with the same height as here should also be P air. So if I go all the way up to here, P3, here is the height. P3 should be bigger or smaller than P2? Should P3 be bigger or smaller than P2 down here? Smaller, good. So it should be smaller, so I need to subtract rho GH. Pressure difference will be rho GH, and this time P3 is smaller, so I subtract it. But P2 is P air. We see there is a pressure difference across this surface. The reason that there's this pressure difference is because the surface is curved. When we look at the surface in a straw, it is flat. So when we look at our system, pressure on top causes a force and pressure at bottom causes a force. We can take our system to be really narrow so that the mass of it doesn't matter. So the pressure across two surfaces will be the same. But when we look at a curved surface will have surface tension causing tension, and this tension will have an upward component, so that the pressure on the top and the pressure at the bottom does not need to be equal. They need to have a pressure difference such that combining with surface tension, you get a zero net force. That's the reason why curvature and surface tension together will cause a pressure difference across the interface of water and air. Now, pressure is force divided by area, right? Here we learn that the capillary force is 2 pi r times gamma cosine. The area of this capillary is pi r squared. So if I want to derive the pressure difference across this surface, I just divide the force